for the nice introduction, and good morning, good afternoon, and good evening to everyone. So let's start this lecture by saying which are the goals of the lecture and the assumptions that we will make. So we will give an introduction to the field of numeric AI planning, in which we try to give a clear definition of the problem that we will treat. We will present the main representation language for this class of problems and the main planning algorithms and systems that support numeric AI planning. In this lecture, we will focus on the so-called state-based model of planning, which makes some stronger assumptions, such as that time is not explicitly modeled, it's discrete, and actions don't have a duration; they are instantaneous. Of course, we can then extend this model to include also temporal information, but to have the lecture clear, we will consider only the numeric information in this presentation. We have also full observability of states, so agents knows the agent knows exactly the initial state of the problem, and it knows also exactly what is the state after the execution, the application of an action. Effects are deterministics, and in the world, the only changes that can occur are the changes that are determined by the actions of the agents. These assumptions can be relaxed, as I said, but in this talk, we will focus on these assumptions. So the lecture has four main parts. The first two parts, I will talk about the first parts, and Enrico will talk about the last two parts. So first, we will define state-based numeric planning, and then we will describe how we can represent this class of problems through languages, and in particular, we will focus on the version 2.1 of PDDL. And then we will describe techniques for solving numeric plannings, focusing on the approach based on heuristic search. We will mention also other approaches, but we will focus on heuristic search. And in this context, we will present several heuristics based on the so-called relaxation method. Okay, so let's start from the beginning. Let's say, what is the basic state-based model that is also called classical planning? Here, the main problem is plan generation, and plan generation is seen as a state transition problem, in which we have a finite and discrete state space S, which could be very, very large. It could have trillions of states or more than that. And we have then an initial state, S0, a subset of states that are called goal states, that are the states where we want that the agent will be at the end of the plan, a set of actions A, and then we have some applicability conditions for each action in a state. So given a state, we know which is the subset of the actions that can be applied in the state S. And then we have a transition function, state transition functions, that tells us, given a state and an action, which is the state that we obtain by executing this action in the state, assuming that this action is applicable in that state. And finally, we have for each action applied in a state, a cost of executing this action in the state that typically is greater than or 0. A solution to this problem, this transition problem, is a sequence of actions that are applicable, starting from the initial state, that transform the initial state, or that maps the initial state into a state that is a goal state. This path, this sequence of actions is optimal if it has the smaller possible cost to reach the goal. This is the very classical formulation and the very classical problem. There are many interesting and important related problems, such as checking the existence of a plan without computing the plan, validating a plan, revising a plan, recognizing the goal of an agent given some actions that is executing, and mixing planning and execution. We will focus on plan generation. So the definition that I gave before is quite abstract, and we cannot use it directly to plan because, as I said, we have a huge, can have a huge state space, and this transition system cannot even be written in many cases. So we need to represent the problem at a higher level, at a more abstract level. So here we start talking about planning languages. First of all, we'll talk about what is a propositional planning language. So that is the language that we can use to represent the classical planning problem. So here states are not just names, but they are described by propositions that are logical atoms or Boolean variables, also facts. They're also called grounded predicates. Then we have a way of describing in an implicit way the transition, the state transition functions gamma, and a way of describing, together with a way of describing the actions through preconditions and effects of the actions over the propositions that are allowed in the representation. The first, probably the first language or that has been developed in the literature is STRIPS, that stands for Stanford Research Institute Planning System. It was developed at Stanford, at SRI, I think. And so a problem in STRIPS language is a tuple where F is a set of all possible atoms that can be expressed in the problem. A is a set of actions. I is a subset of all of the atoms that specifies the initial state through the closed world assumptions. That means that every atom that is not mentioned in I is assumed to be false. We need these assumptions because we are in the case of full observability. And then we have a subset of F that are the goals that we want to reach. So we want to reach a state. We don't have to specify all the states that are goal states. We need to reach a state that satisfies the goals G. Note that in this formulation, we have not specified the states. The only state that we have explicitly specified is I, the initial state. All the other states, they could be trillions of states, are implicit in the description of the initial state and the actions, because through the actions we can reach, through the execution of the action, we can reach other states, and all the states that we can reach defines our state space. Actions are described in strips with positive effects and negative effects regarding the effects, where positive effects are facts or propositions that become true after the execution of the action, and delete effects are atoms that become false after the execution of the actions. And then we have preconditions that are atoms that should be true in the state where the action is applied. So this is the very basic representation. Then there are many extensions, even in the propositional language that includes, for example, conditional effects, non-atomic preconditions, that is arbitrary formulas, domain axioms, state trajectory constraints, and so on. But for simplicity, we will not consider this feature of the language in our presentation, our short presentation. So this was propositional planning. Why do we want to have numeric planning? Well, numbers are very important, very useful for modeling many real-world problems where we need to plan with a limited amount of resources, for example, where we want to model physical quantities like temperature, velocity, pressure, and so on. Or we want to deal with the special information, and we have to represent position of our agent in terms of Cartesian coordinates, GPS position, or we want to talk about consider the size or the volumes of some areas or some object that we are managing in our, we have to manage in our plan. So we need to add numbers in the planning model as well as in the planning language that represent the planning problem. And we want to add something like this in the in our description of the action. We want to add, for example, that before moving, the fuel level should be greater than a certain lower bound, like 100, and that after executing, after applying the moving action, the fuel level is reduced by 88.5, for example. So we also have numeric goals in addition to the propositional goals that, for example, requires that not only we want that the target location is visited in our logistics problem, but we want to also that at the end of the plan, the fuel level is at least 10, just to give a very simple example. Okay, so let's go back to the basic state-based based model for planning that and enrich it with numerical information. What are the most significant changes? The most significant changes are that, first of all, the space of the states is not finite anymore, because since we have numbers and typically we use rational numbers, we can have an infinite set of states in our problem. Then we have states that are not only propositional states, but are numeric states, and we have an initial numeric state. We will describe more in detail what is a numeric state later soon. Then we have a potentially infinite set of goal states, not just a finite set of goal states, while the other things remain the same, except that the transition function now is not finite in the sense that we can have a potentially infinite number of state transitions. This is obvious because since we have an infinite number of states, we can have an infinite number of state transitions. And so the graph is really that the graph of the transition system that represent the basic state-based model for numeric planning is not even readable because it's too large, it's infinite. So now we ask ourselves, how do we represent such an infinite state space and the gamma and the action precondition and effects? Okay, so this leads us to the main representation language for numeric planning in our community, at least at the moment, that is PDDL 2.1. Okay, so PDDL 2.1 is just one version of a series of various versions of PDDL. PDDL, you probably, I'm sure that you have seen this language in previous lectures or labs, is the planning domain definition language, and it is the mostly used language in the planning community at the moment. It's a standard language that was first introduced by McDermott about 20 years ago, and then it was refined and enriched, extended with new features, until the last version that is PDDL 3.1. In PDDL 2.1, there was the introduction in the language of numeric planning and temporal planning, alone or combined, so metric temporal planning. In this talk, we focus only on the numeric part of PDDL 2.1. I should say that there are other versions, enhanced version of the language like PDDL Plus and PDDL 3 that have additional features regarding numeric planning and numerical information. We can include the numbers in the specification of exogenous events, processes, soft goals, state trajectory constraints. But given the limited time that we have, we decided to focus on the core of numeric planning. And so we will skip the advanced features of PDDL Plus and PDDL 3 in this presentation. Okay, so let's focus on PDDL 2.1 and what is the class of numeric problems that we can present in PDDL 2.1. Problem here is a tuple where fx a as 0g, where f is a finite set of Boolean variables, or before we call them propositions. X is a numeric, x is a set of numeric variables typically over the rational numbers, and these variables are called numeric fluents. A is a set of actions as before with preconditions and effects. S0 is an initial problem state. That is a numeric state this time because we have both Boolean variables and numeric variables. So in general, the variables are numeric, and a state is an assignment of values to all the variables of the problem. And then we have a set of problem goals that are that have a propositional part that is the same as in classical planning, plus a numeric part that is specified through some conditions over the numeric variables of X. Okay, so let's go more in detail, and because this is a very general definition, in order to classify, to describe in a more precise way the class of numeric problems that we can support, we can deal with the language PDDL 2.1, we need to see how we can, how actions are represented. Okay, actions have precondition and effects. We have the same kind of preconditions that we have in propositional planning and the same effects that we have in propositional planning, plus numeric preconditions and numeric effects. So the numeric preconditions are conditions on the numeric var that are restricted to be of the form xi rel k, where k is a rational number, xi is an arithmetic expression, and rel is a relational operator, less than or equal, less than, equal, and so on. The effects, the numeric effects, are changes to numeric variables of some particular form. They can increase or decrease a numerical variable. They can assign a value to a numerical value through this value can be specified by an arithmetic expression. They can scale up or they scale down by an arithmetic expression the current value of a numerical variable. Of course, since in this context, as actions are instantaneous, we need to guarantee that effects do not conflict the effects of the same action. So, for example, it is forbidden to have two effects that one decreases the value of a variable and the other one scales up the value of the same variable, because the order in which we apply them changes the global result. And under the assumption that effects are instantaneous, we need to guarantee that any order of the effects produces the same global results. Okay, so there are some restrictions that to avoid this kind of conflicts. Then problems, the goals are again as in propositional planning, plus some numeric goals that are equivalent to the numeric conditions that we have in the preconditions. Instead of putting this condition in the precondition of an action, we put it in a goal, and we have a numeric goal. Okay, note that there is another difference that should be pointed out between propositional planning and numeric planning. In propositional planning, the effects of an action are independent on the state where the action is applied. We know in advance before planning what are the effects, and they will be the same in every state where the action is applied. While in numeric planning, this is not the case, because if we decrease the fuel by a certain amount, then the result, so the value of the fuel, depends on the value of the fuel in the state where the action is applied. So if we decrease by 10, if it was 40, if it was 50, it becomes 30. If it was 10, it becomes 0. So I point this out because this difference can make the design of the algorithms for planning in the numeric context more difficult than in the propositional case. And we will get back to this in the second part of the talk. Okay, so now let's see a very simple example to put together the things that we have introduced so far. This example was introduced, I believe, by Hector Geffner. It's a very simple example. At the end of the first presentation, the first part of the presentation, I have a more realistic example. But let's use this only to illustrate our context, our concepts. So the task here is the following. We have one or more agents on a map, on a grid-like map, that have to water some plants at different locations using water that is loaded and carried from sources, taps available at different locations. Each agent has its own tank that has a limited capacity. So when the agent loads the tank, he has to use also a smaller container, because it cannot put the container directly under the tap. And so he needs to do multiple load actions. Each plant needs its own amount of water, and each move of the agent and each load and unload of the water has some cost. Okay, so we need to formalize this problem in PDDL 2.1 and then use a numeric planner to solve it. So now I'll go a bit fast here because I believe you have already seen this, but let's see how we specify an action in PDDL 2.1, a numeric action for this problem. As you probably already know, in PDDL, we can specify the objects of the problem, and these objects have also a type here. In particular, we have agent 1, agent 2, and so on, that are of type agent. Then we have predicates. That is a way of describing what I call the Boolean variables. We have predicates with the parameters, and once they are instantiated with the objects of the problem, they give the propositions or Boolean variables of the problem. So here, for example, open T, where T should be a water source, is instantiated with open tap 1, and open tap 1 is a Boolean variable. Then we have functions, a particular class of functions that are used to specify the numeric fluence or the numeric variables. And again, we have these functions with the parameters, and once the parameters are instantiated with objects, they generate the numeric fluence. Like, for example, here we have two numeric fluence to represent the position on the grid map of the agent, X position and Y position. So X pos 1, agent 1, Y pos agent 2 are two numeric variables. And what about the actions? So in PDDL, we don't specify single actions, but we specify classes of actions or schemata of actions or parameterized actions. So we have the name of the actions and the parameters. And again, once we instantiate the parameters with the objects, we obtain the real actions. So each of these class of actions is a set of real actions of the problem. And here, for example, we have one, let me see if I can do this. We have one propositional condition or precondition that this is the action to load the water. The water source T should be open, the tap should be open. Then we have two numeric conditions to specify that the position of the agent is the same as the position of the water source T. The X position should be the position of X of T, and the position of A should be the position of the Y position of A should be the coordinate, the Y coordinate of T. Then we have a condition that says that we can make the loading of the water only if the agent is not already carrying the maximum amount of water that it can carry with its with this tank. Because since the load water loads 1 liter at a time, we need to guarantee that the current amount of water that we are carrying plus 1 is less than or equal the maximum load. Maximum load is again another numeric variable, but is different from the X position and carry because it's going to be static. No action will modify the initial value of max load. And the effect of this action is increasing the numeric variable carrying by 1 and increasing the total load of the water during the life of the agent by 1. Okay, now let's go back a little bit on the semantics of numeric planning in PDDL 2.1. Okay, first of all, when an action is applicable, but that's the same as in propositional planning, an action is applicable in a state S if its preconditions are satisfied in the state S. An action A applied in a state S generates a new state S prime, where the variable values of S are changed according to the effects of A. Okay. An applicable sequence of action is the following. It's a sequence A0, A1, AN minus 1 of applicable actions is a sequence of actions so that A0, the first action, is applicable in the state S0, typically the initial state S0, and each action AI in the sequence is applicable in the state SI that is generated by the application of the previous actions in the sequence AI minus 1 in state SI minus 1. A valid plan or a solution is a sequence of actions A0, A1, AN minus 1 that, when applied in S0, generates a sequence of states S1, S2, Sn, such that the last state Sn implies, or in the last state Sn, G holds. So it implies all the G, or G is true in Sn. It's the same thing. Okay, plans can also be not just sequences of actions, but they can also be sequences of sets of actions, forming a sort of non-linear plan. In order to have a plan of such a form that is valid, we need to guarantee that every pair of actions in each set do not interfere, and every pair does not interfere. The notion of if the interference is formally defined, but I'm not going to give you all the details because it's a bit intricate, just the high-level definition. We have that A interferes with action B if an effect of A modifies the values of a variable involved in the precondition of B. And we have also that the effects of the action A do not commute, or the effects of the action A do not commute with the effects of B. So if we are in one of these two conditions, we say that A interferes with B. The second case, for example, let's illustrate only this. We have that if action A assigns 0 to X, we cannot have the other action that assigns y to x to y, again because the results is not the same if we order these effects in a arbitrary way. So depending on the order in which they are applied, we have different global effects. Okay, so in PDDL we have also the notion, way of representing the notion of plane quality. That is again through numeric variables. We can have single numeric variables like total cost that initially is set to 0, and it's incremented by a certain amount by every action in the plan through the effects of the actions. And the goal is to minimize. Well, the objective function to optimize the plan quality is to minimize this numeric variable, this total cost. Or alternatively, we can have, instead of total cost, an arbitrary numeric expression, an arithmetic expression that involves more than one numeric effluent, and we want to minimize this numeric expression. Okay, I go a little bit fast because time flies. What about the complexity of numeric planning? In general, numeric planning is harder than classical planning and propositional planning because it's not even decidable. It is semi-decidable. And intuitively, this is because numeric planning problems could have plans that have no bound on their length. Okay, so suppose that we have an action that increments a counter, and there is no upper limit on this counter. We can keep adding, and indefinitely. So the plan can be as long as we want. And in principle, we could solve the problem if it has a solution. Where a solution should be should have a length that is finite, right? And so we could just enumerate all the sequences of actions, starting from sequences of length 1, on length 2, length 3, until eventually we find a plan. If the plan exists, we will be able to find it. But if the plan does not exist, this enumeration procedure is not going to end. And so this explains very, very shortly why the problem is semi-decidable. So if there is a plan, we can find it in principle, but if the plan does not exist, we don't have a procedure that terminates. If you are interested in more details in this theoretical part, I recommend you to see a paper by Almert when I have a reference at the end of this first set of slides. Nevertheless, there are fragments of PDDL 2.1 that for numeric planning that are decidable. Whether they are useful or not, it's not easy to tell you. It depends very much on the application problem that you have. Okay, there are other interesting fragments that researchers have investigated, and they investigated these fragments because, because they want we want to design algorithms that are effective, that are fast, and that can generate plans of a reasonable size. And so we start with by restricting the language and try to solve the problem, at least for this restricted class of problems. And there are various kinds of restrictions. A particular class of restriction is called simple numeric planning problem that will be discussed in the second part of this talk. Unfortunately, even this restriction is semi-decidable, but here we have algorithms that can find a plan when the plan exists, and to some extent also to prove when it does not exist, but not in general, because the problem is not decidable. So, for example, we constrained that C in a precondition is a linear condition. The assign effects are excluded. Also, the scale up, scale down effects are excluded, and we can increase or decrease certain variables only through constants and not through arbitrary arithmetic expressions. Okay, so I'm almost done with the first part of this lecture. In this slide, I have summarized some of the limits, some of the what I think are limits of the language, but not only me. Also, several researchers in the community have pointed out that these are not these things should be improved. And there is some recent research that improves these limits. So, for example, I mentioned just one of these. In a numeric variable in PDDL 2.1 can be undefined. So, in the initial state, for example, if we have a numeric variable x, we are not forced to give an initial value to x. And so we might have actions that have conditions, application conditions, that involve variables that are undefined because they are applied in a state where the variable has no value. And so it's not clear how to evaluate these conditions, whether they are true, they are false, or they are undefined. There is no assumption like a closed word assumption that if a variable, if an expression involving an undefined variable, then the expression is false. Okay? Some people assume this, that, for example, if x is undefined, x greater than 0 is false. But this leads to some logical problem, and so the issue is not solved yet. But in addition to this limitation, there are also, as I mentioned before, several extensions that make the language very, very powerful, because we can combine numeric planning with temporal planning. We can add state trajectory constraints, exogenous events, continuous processes, and the resulting language is extremely powerful. Okay, so the last minutes of this presentation will, the first part of the presentation, will be dedicated to an example that is a real-world example that is also studied in operational research and is the traveling purchase problem, TPP, that we introduced in AI planning with the fifth international planning competition back in 2006. So in this problem we have a set of types of goods, a set of markets M, and these markets sell different types of amounts of goods at different prices. And we have a demand of each type of goods to be purchased and transported to some depot D. Okay, in this figure, we have 5 markets, 2 depots, and 2 trucks that are used to transport the goods. We want to satisfy the demand, minimizing the routing cost of the trucks and the purchasing cost, so the amount that we spend. There are 6 different versions of these domain formalized in PDDL, and the one that I'm going to show you very quickly is equivalent to the original problem that is studied in OR, and is purely a numeric planning problem. So here we have just one Boolean variable that is to represent the position of the truck at some place. We have 1, 2, 3, 4, 5, 6. Sorry, this is a parameterized Boolean variable. So when you instantiate the parameters, you get many Boolean variables. And we have 1, 2, 3, 4, 5, 6 numeric variables with parameters, saying, for example, on sale, good market, says the amount of the good that is sold by the market, the driving cost from two places, from one place to another place, between 2 places, the price of a good at a certain market, because the same good can have different prices at different markets, the amount of goods that has been bought by the agent so far, the request of the good that we have to satisfy, and the total cost that initially is 0. And then we have the objects. We have 2 markets, for example, 2 depots, 2 trucks, and 2 types of goods. Initially, we specify the prices of the goods at at different markets, the amount of the goods that are available at the different markets, the position of the trucks, and the driving cost with numbers between locations. Then we have the amount of goods that have been bought and the request of the goods, and initialization, the total cost 0. In the goals, we have this numerical fluent that says the amount of goods that we have bought, for example, goods 1, should be greater than or equal the request of the goods. And we want to minimize the total cost. Okay, so in PDDL, this is relatively easy to formalize this problem because we have only 3 types of actions: drive, buy all, and buy all needed. Drive is used to move the trucks from one location to another location and increases the total cost by the cost of driving from between the 2 locations. Then we have 2 actions for buying the goods that are different in this sense. Buy all allows you to buy everything that is all the amount of the good that is sold by the market. In order to do that, the amount that is available at the market should be less than what you need. Okay. In the buy all needed, we don't buy everything, but we buy only a fraction of the amount that is available at the market, and that fraction is the fraction that we need to reach the request. Okay, and so in this second case, let's illustrate the second case, we need to guarantee that the market says an amount of the good that is greater than what we need. We need, when the action is applied, the difference between the request and what we have bought so far. Okay, and then the amount of goods that are sold at the market are decreased to 0 in the buy all, and in the second case they are decreased by the amount that we buy at the market. Okay, so in this case it's particularly compact, the representation, and we can use many planners to solve the TPP problem. Okay. In this slide, I have put a selection of references focusing on numeric planning. So that's a series of references that about PDDL, where you can find, for example, in the paper by Helmert, the theoretical analysis. In the book, in the PDDL book, you can find many examples on numeric planning and so on. Good. So now we start the second part of this lecture. Now that we have defined precisely what is numeric planning in the state-based model of planning, we talk about how we solve numeric planning problems. Well, there are many algorithms and many ways to do that. At the high level, very high level, there are 2 kinds of approaches: planning by compilation and planning as heuristic search. Planning by compilation is this idea that is also present in propositional planning, in other kinds of planning, in which we translate the original problem into an equivalent problem that is addressed also by other communities, not only the planning community, and not maybe sometimes also not even the computer science community, but the OR, for example, community. And then we use specialized solvers for the equivalent compiled problem. So, for example, SAT is a target of the compilation of propositional planning, and satisfiability modulo theory is the target of the compilation of numeric planning. So we can use solvers that for satisfiability modulo theory to solve the numeric plan after we have compiled the numeric problem into an SMT problem. The other approach that we are going to describe in this lecture is planning as a heuristic search, where we use a methodology that is very well known, and that is the general search algorithm, problem solving. But the difference with the general algorithms like best, first star, A star, local search, the main difference in planning is that the heuristic is fundamental, of course, but it's not domain specific, because we want to do domain independent planning. So we want to have heuristics that are very powerful because they are essential for search algorithms, and they are domain independent. And in this second part of the lecture, we will focus on general search algorithm with domain independent heuristics for numeric planning, using the state-based approach, because we can do heuristic search in a space of states, as we have described it so far, or also in other kinds of spaces, like the space of partial plans, where the search here is as the goal of modifying incrementally a plan until we find a plan that's a valid plan. An example of this second class of approaches is the LPG planner that my group developed several years ago, and it was a successful planner. But most of the work in the planning literature focuses on the state-based search. So we decided to focus on especially on this approach. Okay, so it's time to leave the presentation to Enrico, who I hope is here.
Yeah, I'm here. I'm gonna share my screen. Okay, we need to hurry up because time is tight. Yeah. So, okay. Okay. So you see my slides, right? Alfonso, you see it?
Yes.
Yeah, okay. So in this part of the lecture, I'm gonna try to give some basics for actually building a numeric planning system. I'm gonna focus, as Alfonso was saying, on solving numeric planning problem through heuristic search, and in particular through forward state space heuristic search. So state space heuristic search, from a very informal point of view, is about iterating over a set of candidate paths, okay, into a transition system until either you don't have any new path to explore, or you have found actually a path that is a valid solution for your problem. The variant in which that is called forward state space search, it is state space search, but it is conditioned to the fact that you always start from some initial condition. Sorry. Okay, so solving planning problems through forward state space search means having the ability to map, okay, your problem into the underlying transition system. And as we have seen before, this is quite straightforward for the class of problems that we are interested in, and also for numeric planning. And there are a few expedients that you can use because you are solving a planning problem. And among these expedients, there is the fact that you can focus only on reachable sequences. This is due to the fact that you always start from the initial state, so that you can simulate the possible futures by only applying the actions that are actually applicable from some condition. So you don't need really to explore all the paths into the transition system blindly. You can discard loops. This is because in classical planning, we can focus on what are called simple plans or simple paths. and this is due to the fact that each state in any plan, each state does not need to be visited more than once, because we only predicate over state and not over trajectory of states. And of course, you don't want to construct the whole transition system up front, but you need to have a way to construct this transition system in an incremental fashion. One way to navigate the state space is by using algorithms which are called the best first search algorithm. Best first search algorithms are based on using a priority queue that contains all the plan prefixes that you have explored starting from the initial state, and those plan prefixes are implicitly represented by a node with the pointer to its parent, recursively till the initial condition. And this best first search algorithms operates this priority queue in two ways. They pop from this priority queue the next state the next node to be visited according to some function f, and we're going to see what this function f is, or they can push a new node into the priority queue by appending nodes to the plan prefixes that have been explored at that point. So this algorithm does a number of iterations, okay, and it stops when you either find the plan or the plan prefixes are finished and your problem is not solvable. So even if numeric planning, for instance, is non-decidable, if the state space is actually finite, we can still prove either that there is a plan or that the problem is not solvable. So depending on how you choose this function, you can have different algorithms starting from this basis. You can have uniform cost search when your function, that is the function that order which node has to be taken next, is just the cost from the initial state, which is this function g. When the function f that orders the node is just the function g, you have this algorithm. Or you can have, for instance, a star, when in this function you sum to this function here another function that is called the heuristic function, that is a prediction that predict how distant the goal is. Now, applying this approach in numeric planning problem is straightforward. It's straightforward because you just need to extend the representation of the state to keep track of the variables that are in your problem, the numeric variables, and you need to extend the successor function so that the successor functions know how to interpret your numeric planning instance. The successor function will evaluate all the actions that are applicable in a state and will compute the successor of a state according to the action effects of the actions. And then you need to have, of course, the ability to test the goal, which basically involve having the ability of reasoning over this numeric structure here. So really, taking this general algorithm, what you need to do is to change this function successor here and to change the goal state check, which is this check here, to apply numeric planning blindly. Now, if we take the example that Alfonso was presenting before, the plant watering problem, you can see what's called a search tree for this problem. So in this search tree, which is the set of all plant prefixes that the algorithm has explored, you can see that each node is a particular state, contains information in a particular state, and nodes are connected through these actions. So even for this simplified version of the problem, where I'll recall what the main task is, you have this agent that has to pour this plant here, and it needs to get some water from the tap in order to pour the water. So you need to keep track of all these variables, basically here, that are represented using numeric fluence in PDDL, even if for this, even if you have this small problem that you just need to move twice on the right, and then you need to go down, and then you go to the plant to do the pouring, the search tree can be already quite involved. So in general, the complexity of this approach is related to the number of iterations or the size of the search tree that you need to explore in order to solve the problem. And of course, in numeric planning, since the transition system is infinite, the number of iterations can be huge. What is important to boost performance is to have a good way to rank, okay, the plan prefixes that you're gonna see in the next. So the function f, which was the function that was selecting the best node here, is the key parameter that needs to be modified in order for the performance of this class of approach to be acceptable. So of course we cannot change the action cost, which are accumulated through the G function, but we can change the way we predict how distant the goal is, and use an informed search strategy, informed best first strategy such as A star or PD best first search or WA star. That is, we can change the heuristic. So it is known that if the heuristic in particular is perfect, which means that for each state you encounter, it always gives you the exact distance to the goal. The number of expansions, so the number of time that you're gonna expand the new node from the priority queue is linear, okay, with the length of the solution. So the closer, it is known that the closer the heuristic is to the perfect estimate, which is called also H star, the less is the number of expanded nodes. So most of the research in planning and in numeric planning adopts the forward state space search schema and looks into making heuristic functions as much precise as possible. So from a formal perspective, an heuristic is a function that maps states into a rational value and an infinity value. And this function is said to be admissible if it always underestimates the actual, if it never overestimates the actual distance to the goal. And if you have this property and you use a star with some tweak, you can always find optimal solutions. Then we say that the heuristic is self-pruning if whenever the heuristic tells you that the problem that the heuristic is infinity at that point, then it is actually the case that there is no solution from that state onwards. And also we want the heuristic to be tractable, okay, because we want that the heuristic is easier than the problem that it is actually trying to solve. Otherwise, it will defeat its purpose. So there are, so we need to define heuristics for numeric planning. How do we do that? So of course we can have the user that defines the heuristic. This can work well in some problem because the user can know a lot about the problem, but it's not really general. So so we can. Sorry, I'm looking at the. Yes, that's true. The comment. Then we can construct, or we can construct an algorithm that can look at the problem and tell us what the value of the heuristic actually is, and we can do this automatically. So heuristics of this kind are often called domain-independent heuristics, and we're gonna see how we can build domain-independent heuristics for numeric planning by investigating their property about admissibility, self-pruning, and tractability. So the way we devise heuristics for numeric planning follows the idea of using a relaxation of the problem that we are interested to solve. This relaxation is based on the idea that you start from the problem that you are interested to solve, in this case numeric planning, and you define a new problem that relaxes the problem that you're interested to solve. By making sure that the arising relaxed problem is easier, but still contains enough information. Then you solve the relaxed problem and use the solution.
Okay.
What's this slide here? You hear me, Michael?
Yep, I can hear you. I think that was the last slide.
Yeah, okay. Yeah, so I was talking about how to devise heuristics. So what are relaxation-based heuristics? So relaxation-based heuristics are heuristics that are devised by using this principle of devising a new problem that is actually a relaxation of your problem, and this new problem has to contain enough information to actually approximate the problem that you're interested to solve. Of course, this relaxation has to have some property. It has to be easier to be solved in order for being useful. In numeric planning, there are two relaxations that have been investigated in the last I'd say 20 years. The first relaxation is called the interval-based relaxation. The main idea is that you will construct this relaxation by decomposing or ignoring any interactions that happen between the numeric variables of your problem. And this relaxation is characterized by really reasoning by starting from the initial state up to the point in which the goal is satisfied. And then there is another relaxation that is called the sub-goal-based relaxation that still uses a decomposition principle, but applies this decomposition principle to the sub-goals of your problem. And it is not characterized by starting from some initial state, but by starting from the goal condition of the problem, up to the point in which all what are called action supporters have been found. Both this schemata can be, both frameworks can be used to devise a variety of heuristics. So in an interval-based relaxation, very intuitively, you map all your numeric state variables into a set of into intervals, each variables into an interval. So for instance, you start from the initial state where you have the degenerate intervals that are actually representing only a point. And this representation serves the purpose of representing many states at once. Each state is a particular choice that you make over these intervals. And then you change the semantics of effects through what is called the convex union. Basically, the convex union, very intuitively, is a way to make it possible that every time you apply an action, the set of intervals only grow. For instance, if you have an action that increases the value by 1 and you start from 0, 0, then the next value is going to be that the x can be any value between 0 and 1, and y remains the same. And if you have, for instance, an assignment of a variable x to 5, you need to extend the value of x from 0 to 5 because intervals don't have goals. And then you change the semantics of the formulas so as to over-approximate satisfiability. So you, for instance, if you have a condition that says that x has to be equal to 10, this condition is satisfied in 0, 10. And the situation gets a little bit more complex when you have operations in your conditions. Okay, each operation needs to be computed using a principle that is that of having the result that includes all possible values that can ever be attained by any combination of the values that you can pick among the intervals of your term. You can use for this purpose known results from interval analysis, which is a very powerful framework. You can define arithmetical operations, but also other operations that are outside of this talk. however. And what you can do, basically, you can, the result of these operations are basically a new interval that says what can happen. So what's an enclosure, okay, of the possible values of your variable, or of your expression, if your expression contains intervals. So let's take two examples. So say you have this condition here, x plus y equal to 0. So, and you have a state in which x is equal to 0, 10, and y is minus 15 and minus 15. Is this condition satisfied? No, because there is no value, because if we apply the interval arithmetic for these two intervals, we get an interval in which there is no 0 in this interval. So this condition is not satisfied. And the situation would be different if instead of having minus 15, we would have minus 5. Okay. So the interval-based relaxation can be then formalized as an extended problem, okay, in which so we start from the problem, we change the initial state as a set of intervals, we change the semantics of the action, the goals, the variables remains the same, but they are interpreted in a different manner. And the question is, how do we solve this problem? So there are the main the solution of this problem is done during two steps. In the first step, you do what is called a reachability analysis of the goal, which goes in a forward fashion, and then you extract what is called the relaxed plan from the analysis, from the reachability analysis that you have done, and this is done in a backward fashion. For instance, coming back to the example that we have before, the process is basically a process that develops across different levels, and in each level you have the set of intervals that you may attain by apply actions. You start from a level 0 in which you have the initial state, and you determine the action applicability using the intervals that are corresponding to the initial state, and you apply all the actions that are applicable into this state. You go to a next state in which there is all the intervals are updated, and again you see what actions are applicable, you apply these actions, and you go on and so on and so forth until some goal is satisfied. For each level, you store all the actions that have been used. So the observation for this approach is that all the conditions that are satisfied at some level I will also be satisfied in any level j that is greater than I, and this is because there is some sort of monotonicity in the actions that are applicable. Okay. So the actions are always applicable. If they are applicable at some point, then they will always be applicable in any further point. And this is the main principle for which this thing terminates when the problem is solvable. So all good when the problem is solvable. The problem is when this problem it isn't solvable, and so this kind of issue comes from the fact that we are still in a numeric setting where variables can grow indefinitely. So we need to have a way to understand how to stop this process when, because there could be the case that even in the relaxed version of the problem is not solvable. The problem is not solvable. So this. To this end, there are two analyses that can be done. Just very briefly, one is the so-called MNID criteria that establishes conditions for each variable. It says basically what is the maximum value that a variable needs to attain in order to satisfy all conditions in which this variable is mentioned. And so you can stop when this point, when you saturate basically this criteria. This approach can be adopted in problems where you have only linear expressions and a fragment of planning which is called acyclic planning, where you have assignments that can only be acyclic. and this acyclicity is somehow a way to actually have a means to calculate this maximum need criteria. This is true until 2003. Then it has been extended through another algorithm that proves that with the same approach, you can solve even more complex problem by doing what's called this asymptotic reachability. This asymptotic reachability make the hidden state dependency explicit in preconditions of supporters, which are particular action constructed from the actions of your problem, and so you can determine at the price of a slightly further relaxation, which is meant to break the acyclicity of your assignment. You can prove that the problem is relaxed. That the relaxed problem is solvable or not by applying this algorithm. So how do we actually get the relaxed plan? So we can start from the goal, okay, by looking at the levels that we have developed in the forward analysis, and we can extract, okay, all the actions that are needed for some sub goal until the point in which we go back and we have all the sub goals satisfied in this process. For instance, a relaxed plan for our problem is to to water the plant 5 times, to load the water when we are in the tap, to go 2 times east, go south, and this is a relaxed plan. Is this relaxed plan a plan for the main problem? Of course it is not, but its cost, okay, can be used to guide the search. And the heuristic of metric FF is basically the sum of all the actions that are in this relaxed plan. And this relaxed plan can be computed by back chaining the sub goals in this recursive schema. Okay, interval-based relaxation is computable, tractable, safe-pruning, but it is not admissible. In order to get admissibility condition, we need to move into the framework of sub-goaling based relaxation. So the sub-goaling based relaxation is based on the idea to backward from the goal and recursively over sub-goals that need to be achieved. And you do so by focusing on all the sub-goals in a way that pretend that there is no interaction between the sub-goals that are at a given level. So you start from the goal, you see, okay, what are the goals? The goal is a set of goals. What are the goals this goal consists of? It is G0, G1, G2, G3. And okay, I'll solve the problem for G1. I solve the problem for G1, for G0, for G1, for G2 by using actions that are somehow achievers of this G0. And then I combine these costs somehow. So there are 2 interpretations on this relaxation. One is a pessimistic interpretation in which you sum the cost of all the sub-goals, and the other one is an optimistic interpretation in which you maximize the cost of all the sub-goals that you have attained. This approach that has been invented for classical planning in principle is based on the idea of using regression. Regression intuitively is an operation that combines a given formula with an action and generate a new formula that establishes sufficient and necessary conditions for reaching this formula through the actions. It can be formally characterized, but the basic idea is basically to understand what are the conditions that are needed if I apply this action to get a given condition. In classical planning, if this formula is an atom that needs to be achieved, and you have an action that adds this atom, the regression of this formula through this action is just the precondition of this action. And this is the fundamental for making sub-goaling so effective in classical planning. Having defined that, we can formulate the sub-goaling relaxation through this currents equation that distinguish 3 cases: when the state satisfies the formula, when the state is a propositional this is an atom, or when the formula is a propositional atom, or when the formula is a conjunction. When it is a propositional atom, you just minimize over all the achievers, taking the achievers that minimize this sum here, which is the cost of the achiever plus the cost of recursively reaching its precondition. So now this formulation here gives us an admissible, safe pruning, and tractable estimate. The question is, how do we extend this to consider numeric variables, but in particular numeric conditions? And to answer this question, we focus actually, the only way this has been extended is in the context of simple numeric planning. So simple numeric planning, as Alfonso was telling you before, is a fragment of numeric planning in which all the numeric conditions are linear, okay, and all the actions that interact with these simple conditions are either increase or decrease, but by a constant. So the right-hand side of the actions is a constant, and you don't have assignment operations. And the simple numeric planning is the restriction in which all the conditions are simple. So for this class of problem, this is already okay. So for this class of problem, we can define a regression, and the regression intuitively operates in the following manner. For each numeric formula, so it uses the classical planning framework as a backbone, but when it encounters a numeric formula, it produces a new formula where each variable is substituted with the way such variable is modified by the action. For instance, if you have a condition of this kind and an action where the effects are x plus equal to 1, so increase x by 1, and you have an action where you decrease x by 1, the regression of this formula is for action A, this formula here, and for action B, this formula here. So what can we say? We say that action A actually is a possible, which is a little bit different with respect to the classical case, is a possible achiever for this formula here. And also, it seems that you need at least 10 execution. If you are in a state where x and y are 0, you need 10 execution of A in order to get this formula satisfied. And while for action B, this formula tells us that action B is not a possible achiever for psi, and it can never be an achiever for psi. So this regression finds some kind of necessary condition for an action to be considered an achiever. And these observations are independent on the state in which the actions are applied. So we can reason about the influence of the action, even if the numeric planning effects are state dependent. We can reason about the fact that an action is contributed positively or negatively with respect to the condition. So it turned out that this regression can be extended asymptotically and you can have a complex mathematical formulation which is not really that complex in the end, but it's a manipulation of your formula that can be used to understand the influence of the action after a number of times this action is deemed for execution. And using this formula, we can understand, using this operator here, we have a way to establish whether an action A is a possible achiever by just inspecting the sign of this term here, which is called the net contribution of the action A onto psi. And we have a mechanism to count because we can basically understand in a given state how many times an action needs to be executed. And this is somehow a generalization of what I have shown you in the example before. So this can be plugged into the Hmax heuristic for classical planning, and we can extend it to make it sensitive to the numeric structure of the problem by just distinguish to the cases in which you have numeric condition from the case in which you have propositional condition. And by solving this problem here, you can have an estimate for numeric planning and classical planning altogether. This is safe pruning, it's tractable, it is admissible, it is not admissible. There is a counterexample that I don't have the time to show to you. You can see the slides offline. But the thing is that this term here, in order for this estimate to be admissible, that is to never overestimate the actual distance to the goal, you need to decouple this minimization problem in two terms. One that estimates the number of times an action is needed to be executed in order to reach a condition, and another one that estimates a lower bound on the preconditions of all the achievers of this condition here. So this is a search tree with this H max over a 10 times 10 grid, and this is the search tree, and it does not end here actually, but it was not fitting in the slide for the set when you have the same algorithm without heuristic. So this can be helpful. There is also an inadmissible variant that you can see offline on the slide. So the question is really, is it better subgoaling or interval? It really depends on the problem. We can leave this kind of thing for discussion if you want. And in the slide, you can also find references to work that is not covered here that extend the basics that I have explained to you. And the list of planners available that you can use to try all these techniques, PDDL, numeric PDDL, and things like that. Just a recap, a take-home message. So in the second part, we have seen that we can use state space search pretty much off the shelf in numeric planning, but the heuristic becomes really a crucial aspect. And for this aspect here, you can use, we know two relaxation that can be other, and there is plenty of problems that try to combine these two relaxations, find new ones to understand whether there is some way to capture interactions between the actions, for instance, when you decompose the sub-goals or the variables of your problem. And yes, I think we need to. I need to stop here.
Thank you, Enrico and Alfonso. There's one more question in the chat which is not yet answered, and we have a couple of minutes, so maybe you can answer that.
Yeah. So let me.
So about the convex union relaxation, Eyal asked, is it essentially delete relaxation extended for numerics?
Yeah, it is. So this is the very first work that approached the numeric planning was exactly starting from understanding how to extend the delete relaxation to consider numeric variables. And in the very beginning, it was not understood in terms like using intervals, by using variables that could only increase value of by actions that could only increase the value of the variables. You had to do some machinery in order to get to that representation, but after a few years, we understood that this could be explained by using interval analysis, and that gave us the chance to approach problems more complex than the one that would have that were approachable before.
There is an additional question that has not been addressed yet by Giorgio. About
so I cannot see the.
I see that. Yeah. Actually, I'm not sure how to respond to this, how to answer to this question. Since numeric planning as we do it is actually has a strong assumption about the fact that actions are deterministic. Well, when you move to probabilistic planning, this assumption does not hold anymore. And so combining the two things is clearly interesting, but it changes significantly not only the language but also the kind of problems that you are going to address. So it's an interesting question how to effectively extend or combine numeric planning and probabilistic planning. That also probabilistic planning has numbers, of course. But it's a kind of very general question. I'm not sure how to answer about this.
So yeah, there is
an opinion. It's a kind of high-level question that it's interesting to discuss. It's interesting. Enrico, if you have a position, please go ahead.
Yeah. So it is definitely interesting. It is definitely interesting. There is another language that has been developed in the literature, and it's called RDDL, which can.
I think Scott talked about that in his
Scott Sumner, yeah. So that language supports probabilistic Markov decision. You can model Markov decision process in it. And you can also model numeric variables, but well, you don't have the scalability that you have in the language that we use. Like the size of the problems that you can handle there, it's more limited. So it's about trade-off. It depends really on the application, but it's definitely an interesting question. This one.
Yeah, unfortunately, Scott had no time yesterday to cover RDDL, but indeed it is conceivable and feasible to use numerical variables in probabilistic planning, in particular when combined with MCTS techniques. But there is the scalability issue for probabilistic planning, which is quite general.
Yeah.
Thank you.
Yeah.